Good morning, good afternoon, and good evening. My name is Whitney, and welcome to our second session of our Arista Technology webinar series, Designing and Deploying EVPN VxLAN Networks. Today's topic is Optimizing ARP in EVPN VxLAN. We are joined by Arista's own Alex Nickel, Technical Marketing Engineer, and Systems Engineer Mitch Vaughn. I'm going to interrupt our regularly scheduled content to quickly advertise our upcoming partner exchange because I know we have some partners on this webinar. Arista Partner Exchange 2020 is our inaugural global partner conference dedicated to Arista partners. This exclusive event, themed Client to Cloud Era, the Network Transformation, will be an intimate gathering where you can meet with Arista's top executives, gain access to Arista's roadmap and industry vision, view early previews of joint solutions powering the next generation IT infrastructure for the campus, data center, and hybrid and private clouds, as well as get in-depth technical training that enables partners to accelerate business with Arista. If you are interested in attending, please visit www.events.arista.com/PEX2020. Thank you all, and let's get back to the presentation. We'll hand it off to Mitch.
All right, very good. Thank you, Whitney, for kicking things off. And thank you again to everyone that has made the time to join session number 2 of 6 in our tech series. We can see that today's focus will be on optimizing ARP in EVPN VxLAN. But we also have a nice list of what's coming up next, whether it's dual homing with MLAG, active dual homing without MLAG, scaling. And then last but certainly not least, in session 6, we'll wrap the series leveraging some new standards to enable VRF-aware routed multicast in the overlay. Now, during these sessions, we are broadcasting live to you, our virtual studio audience of fellow engineers and network enthusiasts. So please ask questions via the Zoom Q&A window, and we'll do our best to make this as interactive as we can while still trying to adhere to our 1 hour-ish time limit. As a reminder, the sessions throughout this series will assume that all of the attendees have an understanding of VxLAN fundamentals and operations. And the sessions do build upon the concepts covered in previous sessions. So for example, today, we're going to build upon the topics that were covered in the first section, focusing on the route types and their respective purposes, as well as the different routing modes available to us, primarily asymmetric and the symmetric IRV modes of operation. Just like in our first session, we're going to go through a series of scenarios to really illustrate and discuss today's topic. And speaking of the scenarios, here they are. One thing I'd like to call out with the scenarios out of the gate is that for each respective routing model, instead of just jumping in and saying, hey, this is how we're going to optimize ARP with asymmetric IRB and let's rock and roll, we're going to take a few minutes before we do that and actually review each respective model. And the reason we're going to do that is because the understanding of the operational differences between the two models, and specifically how they relate to forwarding entries programmed into hardware for remote host reachability, is going to be critical today. And that's a bit of a mouthful, but we're definitely going to cover this in quite a bit of detail, because these concepts really do set the foundation for all of our scenarios. Now, the review won't be as in-depth as our first session. So for further details on the concepts or the configuration related to these routing models, we can always refer to the recording from the first session. And the link is right down here in the deck, and we can share this out via the Zoom chat as well, so everyone has it for reference. All right, one last bit of housekeeping. Instead of just jumping right into the CLI with no frame of reference, which is always fun in networking, let's actually take a minute and review the topology itself. The topology we'll be using today is, of course, a layer 3 leaf and spine. As covered in the first session, we do have multiple options for building out reachability within the underlay. Whether it's an IGP or BGP, the end goal ultimately is still the same. Establish reachability between the loopbacks of our spine and leaf switches. Now, in this environment, we've opted to leverage BGP, and specifically external BGP, to provide IP reachability within the underlay, and also establish pairings within the EVPN address family to establish the overlay control plane. Also, just as in the first session, the point-to-point links here really aren't of any interest to us today. They're just going to serve as transit. But what is going to be of interest are the loopback interfaces on the spine and leaf switches. Now, loopback 0 is going to not only uniquely identify each node within the topology, but it also serves as the source interface for the peerings established in the EVPN address family between the leaf and the spine switches. The other loopback down here, good old loopback 1, is going to exist only on our VTEPs. And that's because it'll serve as the source and destination of the VxLAN tunnels. So when we perform our packet captures to validate the data plane, the address associated with this interface is what we're going to see in the outer IP header of those VxLAN packet captures. Last few bits of information here. The leaf switches are where we're going to spend most of our time from a configuration standpoint, primarily leaf 1A. Now, we'll occasionally use the spines for packet captures and some control plane state validation, but we're primarily going to spend most of our time kind of where the magic happens on the VTEPs, the leaves themselves. Now, in the interest of time, the environment has been pre-configured in an asymmetric IRB model on the leaves. And this really sets the stage for the first scenario. So without further ado, let's go ahead and jump right into the review of the asymmetric IRB model. All right, so in this example, a pretty straightforward use case. Host A wants to ping host C, nothing too fancy. Both VTEPs are configured with the asymmetric IRB mode of operation from a routing standpoint. What this means is that host A is going to send his echo request wanting to ping host C to his first hop gateway. Once it reaches the first hop gateway, which resides on leaf 1A, leaf 1A will actually perform a local routing operation into the destination subnet. Once that local routing operation has been completed, then leaf 1A needs to perform a VxLAN bridging operation via L2VNI 10030, which is associated with the destination host's respective bridge domain, towards leaf 2A 2B, which behind the scenes is a pair of VTEPs in an MLAG configuration. So the VxLAN packet is actually going to arrive here on leaf 2A 2B. They'll take a look at the L2VNI and then know that they're going to perform a bridging operation based in whatever broadcast domain, whatever bridge domain is mapped locally to that VNI, which in this case we can see is going to be VLAN 30. So leaf 2A 2B, they perform decap and then send the echo request to host C. And then ultimately the same thing happens in the reverse direction. Host C sends the reply to its first hop gateway, the local routing operation occurs, and then a VxLAN bridging operation towards host A is going to occur via L2VNI 10010. A couple key points here, and we're going to validate this via packet capture here in a second, but a couple key points is that on the way there, we used L2VNI 10030. On the way back, we used L2VNI 10010. And a key takeaway here is that in the asymmetric IRB model, we need to make sure that the local bridge domain, as well as its associated gateway, in this case, VLAN and SVI, that both the source and destination of the communication, that the bridge domain and SVIs exist on both of the VTEPs involved in that communication. In other words, SVI 10 and 30 exist here, SVI 10 and 30 exist here. And we need that so that that local routing operation and then the bridging operation can occur. All right, so let's actually take a look at this on the wire. And then after we look at it in our packet capture, we're going to circle back and talk about how this relates to the actual forwarding entries created in hardware in this model. So when we actually perform our packet capture, we want to make sure that all of the packets go through spine 1. We're going to run our capture on interface 1 here. So what we'll want to do is we'll take spine 2 out of the game, but instead of shutting down the interfaces, which would certainly work, or shutting down BGP, we're going to take a more graceful approach, and we're actually going to enable maintenance mode on spine 2 to take it out of the data plane path. So over here on spine 2, I can go ahead and take a look and actually show the configuration here. The configuration we're going to put in here is just, we want to enable maintenance mode for the following BGP peer groups. So we want to notify the peers that are part of these peer groups that, hey, we're going to go down, we're going to be taken out of the game here, go down for maintenance, whatever it may be. And the way we're going to do that is Spine 2 is going to apply the graceful shutdown or G-shut community to the BGP updates that it advertises to its respective peers in these groups. And actually, to show this in action, let's actually do this. So we'll run a watch command over here on leaf 2B. And right now we can see that to get to leaf 1A, we could either go via Spine 2 or via Spine 1. Let's go over to Spine 2, and this time we'll actually apply the configuration to take them out of the game. If we go back to leaf 2B, we see we only have one path now. Now we only have one path, but if we look at our BGP peerings, they're still established in the IPv4 address family, as well as the EVPN address family. I'm just going to give you a little bit of an idea what's actually happening behind the scenes. If we do show IP BGP for 2221, when we look at the detail, we can see that the G-shut community has been added to this update that we received from Spine 2, and the end result of that was make the local preference look terrible, aka 0. So this loses. It's still there, it's just not the best path. So I wanted to provide a little bit more detail rather than just saying, hey, let's take them out of the game and enable maintenance mode. So now we have a little bit of an idea as to what was actually going on behind the scenes to make that happen. And we can do our packet capture now because we know with confidence that anything destined to or coming from 2221, which is loopback 1 on leaf 1A, is going to go through Spine 1. So back to our scenario, let's level set. Host A is going to ping host C. And we know it's going to be the asymmetric IRB model, and we want to validate our understanding by looking at what's on the wire. So on host A, we'll get our ping ready to go. And then over here, we'll actually execute the packet capture remotely, and we'll bring the packets back to our local workstation here and pipe the output to Wireshark. So actually authenticate. And we'll see here that there's going to be a bit of noise. Yes, running BFD, so the BGP stuff. Let's apply a filter and cut some of this noise out. And then we'll execute the ping from host A. And we'll just let a few pings roll here, maybe 2 or 3. And then we'll kick back over and take a look at what are we seeing on the wire. So going through the packet capture, just reviewing, what do we expect? The inner IP header is source and destination of host A and host C, as expected. The inner Ethernet header has a destination MAC address of host C's MAC address. And the reason being is that we're performing a VxLAN bridging operation via L2VNI 10030 directly to host C's MAC address. In the outer IP header, as expected, we see the source and destination VTEPs. And just as we whiteboarded out in our scenario, the reply is going to be the same, just in reverse. So source of C, destination of A, VxLAN bridging operation via L2VNI 10010, destined to the MAC address of host A. So we've validated our understanding here by looking at the wire and saying, okay, we understand how asymmetric IRB is working. But then the question becomes, what does this mean to us from a hardware resource consumption standpoint? So let's actually stop the packet capture and take a look at this. To make things a bit more interesting, we've added a lot of hosts into this example, and we have a new pair of VTEPs, 3A and 3B. We'll focus in this scenario, host A is pinging host C110. As we saw in our packet capture, we know that when this happens, because leaf 1A and all the VTEPs are operating in the asymmetric IRB model, we know that the L2VNI is going to be used in the VxLAN header, and that the destination MAC address is going to be the remote host's MAC address, the target host of this particular ping. Now what that means is that if we have 250 hosts behind this VTEP pair and 250 hosts behind this VTEP pair, at any given point in time, leaf 1A may be required to perform a VxLAN bridging operation directly to any of these hosts. Meaning, in other words, it'll need to actually maintain 500 unique entries, forwarding entries in hardware in order to perform the VxLAN bridging operation to any known remote host. So let's actually take a look at the ARP table in our environment and see this in action on some of the VTEPs. So we go on Leaf1A and we do a show IP ARP for VRFA. We see that, as expected, we have all of the locally attached hosts. We have an entry for them in this table. Additionally, for the remote hosts, which we know about because of the type 2 routes originated by the VTEPs where those hosts reside, we understand the MAC IP mapping for those hosts as well. And we're maintaining a unique entry for each of them. So this is the one-to-one mapping that we just reviewed. And in the asymmetric model, the VTEPs, of course, need these forwarding entries to then be put into hardware, since a bridging operation is used to reach each remote host. Now, we can filter this output if we want. If we only care about seeing what hosts are actually remote, we can just do a show IP ARP remote and take a look at that and see, okay, well, we have the MAC plus IP bindings for these known remote hosts in the environment. But the question ultimately becomes, what if a remote host is known, but it's not communicating with any of our locally attached hosts? Do we really need to maintain a forwarding entry in hardware for that remote host? And if the answer is no, we do have the ability to only program forwarding entries into hardware for remote hosts that are communicating with our locally attached hosts. And this feature is referred to as selective ARP. Now, even when we enable this feature, which we'll do in a second here, we still maintain the MAC plus IP mappings for all of the remote hosts in software. And we'll use these mappings for functionalities such as ARP suppression, ARP proxy, which we'll cover in a few of our last scenarios. But the idea is that these mappings won't consume hardware unless they represent a remote host communicating with our locally attached host. So to see this in action, let's actually go ahead and clear the ARP cache on all of our end hosts. And let's actually open up a second session to Leaf1A. And the reason we're going to do that is we can actually just do a watch command and take a look at the impact of actually enabling this feature on Leaf1A. So under router L2 VPN, ARP selective install, we see now that we only have only the hosts that are locally attached are shown in this output now. Now, as we covered a second ago, we still know of the remote host MAC IP bindings. They just don't show up in this table, and they don't get a unique forwarding entry programmed into hardware unless they actually communicate with a locally attached host. So let's actually put this to the test. Host F will ping host C. And if our understanding is correct of this feature, what we should see is that Leaf1A will then have an entry populated in this table for host C's MAC plus IP mapping. So here, ping 30303100, and we'll just repeat it 10 times, that's plenty. So the pings are running. If we look back at Leaf1A, now we have the entry. So as far as optimizing the hardware resource consumption in an asymmetric IRB model, this goes a long way to accomplish that, and that we're only going to, again, program forwarding entries into hardware for remote hosts that we know about and are actually communicating with locally attached hosts. Okay, so that actually wraps up our first scenario. Instead of just kind of jumping directly into the symmetric IRB model and the techniques we have to actually optimize ARP in that model, let's take a look at some of our findings here. So in this model, we see that, again, the VTEPs always perform VxLAN bridging to remote hosts. We saw that with selective ARP disabled, we have the one-to-one mapping, and there's a unique forwarding entry programmed into hardware for each remote host. When we enabled selective ARP, we only programmed forwarding entries for remote hosts communicating with locally attached hosts. So it's still a one-to-one mapping, but we get a chance to actually optimize our hardware resource consumption. Okay, so before going any further, I would like to pause for questions. So Alex, Alton, any outstanding questions out there that we should address?
Hey, Mitch. Yeah, there was one. There was one question just regarding timers and how we are actually refreshing timers. Do you want to cover a little bit about that in terms of Macs and then the ARPs themselves?
Oh, absolutely. So as far as the entries that are populated in the local ARP table, those are derived, good question, those are derived from the type 2 routes that we've received via BGP. So let's actually go back here and take a look at our topology. At some point in time, there was a type 2 route originated via either 2A or 2B for host C. That route arrives on leaf 1A, he imports it into the proper MAC VRF, into the proper bridge domain, and then both the MAC address table and the ARP table can be populated based upon that BGP update. And those entries can stay there until the BGP withdrawal message is sent via BGP for that particular host. Does that answer the question, or Alex, do you want to add anything more there?
No, I think that answers the question. Thanks, Mitch.
Yeah, no problem. All right, any other questions, or are we good to keep on moving?
I think we're good to keep on moving.
Okay, cool. So next up, we have symmetric IRB. And just as we did with asymmetric, we'll do a quick review and validation of the symmetric IRB model and ultimately how it relates to hardware consumption. So same scenario, host A in this case wants to ping host C. Again, nothing fancy, we just want reachability between these two hosts. Now, just as in the first scenario, host A sends its echo request towards its first hop gateway, which resides on leaf 1A. Now, this is where the difference is between symmetric and asymmetric. Instead of leaf 1A routing directly into the destination subnet, it's actually going to perform a VxLAN routing operation via L3 VNI 50,001 in this case, towards the next hop VTEP that has advertised reachability to that respective host. In this case, host C. Now we're gonna break down that statement because there's a lot in there. Like, how does it actually pull this off? So we'll do the packet walk, and then we'll take a look at it on the wire and really see the different components that make this happen. So again, leaf 1A is actually going to perform a VxLAN routing operation via L3 VNI 50,001 towards leaf 2A 2B. Once leaf 2A 2B receive this VxLAN packet, they look at the L3 VNI, and that's what provides signaling to them as to which VRF they should perform the local lookup and forwarding operation in when they route into the destination subnet that they see in the inner IP header. So in other words, because 50,001 is associated with VRF A on leaf 2A 2B, they're going to perform the local routing operation into the destination subnet of 30.30.30/24 within VRF A. Once they perform that local routing operation, then it's ultimately just bridged down to the destination host. So the big change here is it's a couple things. The originating VTEP and the destination VTEP in that case, we do not need the local bridge domain or its respective first hop gateway, like any L3 presence on that bridge domain, on either the source or the destination leaf. In other words, leaf 1A doesn't need to have VLAN 30 configured nor its associated SPI. And this will still work because we'll see in the control plane, we're ultimately going to follow a host route to get to host C instead of performing a bridging operation directly to host C. So let's actually break this down and take a look at this on the wire. And then we'll kind of take a step back and understand, okay, where does this information come from? The L3 VNI, the actual router MAC, which we're going to cover in a second. Where does this information come from? So host A, in this case, first, let's actually go ahead and enable the symmetric IRB mode of operation. So on leaf 1A, what we're going to do is we're going to remove VLAN 30, and we're going to remove the SVI associated with VLAN 30. So now that those are gone, if we go back here and we go to host A, and we try to ping host C, previously it was working just fine. We're still in the asymmetric IRB model, meaning leaf 1A is receiving this echo request from host A, and it's saying, okay, show IP route VRFA, I have no idea where to go. Destination net unreachable. Because it's trying to perform that local routing operation into the destination subnet. So let's go ahead and change that. Let's actually define a layer 3 VNI, and the way we'll do that is under the VxLAN interface, we'll do a VRF to VNI mapping, which makes this a layer 3 VNI. Now, once this command goes into place, this effectively enables the symmetric IRB model on the VTEP. And what's nice is that this is the exact same configuration on any VTEP that's servicing this particular VRF. So we can go right over to leaf 2A and 2B and say, all right, go ahead and apply the configuration. 2B, go ahead and apply the configuration. At this point, we see that this is working. Okay, it's great that it's working, but let's take a look at why is this suddenly working now. Let's look back at leaf 1A and take a look at that same show IP route command. This looks a bit different. It looks like there's a lot more here now. What happened? Let's actually filter this output a little bit. Show IP route VRF-A, and let's do a grep, and let's just grep for the host routes. We see that we'll focus on host C. He's been a good sport. We'll keep picking on him. So host C is reachable via VTEP 2222, layer 3 VNI 50001, and router MAC ending in 201D. So we haven't really touched on what the heck is the router MAC. And the purpose of this is that this is the MAC address that's going to go into the destination MAC field in the inner Ethernet header. The reason for that is because if we go back to our diagram here, remember we performed that VxLAN routing operation towards this VTEP. When 2A or 2B, whoever receives it, performs the decap operation, we need a way to tell them that, hey, you need to take action and route this packet. This frame is destined to you. So the inner Ethernet header is what does that. In the inner Ethernet header, after decap, leave 2A or 2B are going to see that, oh, well, this frame is destined to my router MAC. I need to take action on this. Then it routes into the destination subnet and then forwards to the host. So now that we've kind of walked through this on the whiteboard and we've seen the control plane state generated by the symmetric IRB model, well, we'll do two things. One, we'll validate our understanding in a packet capture, and then we'll circle back and talk about what this means from a hardware resource consumption standpoint. So let's go back to host A. We know the pings work, and actually we can just leave these rolling. Why not? And we'll go over here and actually start our packet captures back up. All right, again, we'll filter out the noise. And we'll go ahead and stop this and take a look at what's changed. Inner IP header, source of host A, destination of host C. As expected, nothing's really changed there. But the destination MAC address is no longer, the inner Ethernet header is no longer the MAC address of host C. Instead, it's the router MAC associated with the next hop VTEP that has advertised reachability to this host. So when this arrives at 2222, which is a shared IP address between 2A and 2B, whichever one of them performs the decap operation is going to see this and say, whoa, I got to take action. Then the question is, well, I have to take action. I have to route into a destination subnet to reach this remote host. What VRF do I use? L3 VNI 50001 is locally mapped to VRF-A. So, okay, cool. Show IP route VRF-A for this, 30, 30, 30, 100. Okay, cool. I know where the next hop is, and then I can eventually just bridge to that host. But we see in both directions, it's the same model. It's going to be the L3 VNI in both directions, which is essentially where this gets a bit of the symmetric name from. Instead of using the L2 VNI, different L2 VNI in each direction, we're going to use the L3 VNI. Another important takeaway here is that even if we are trying to reach a host in a remote host that's in a subnet that we're directly attached to, we're still going to follow the host route because it just criteria 0 in routing, more specific wins. So if we go here to leave 2A, show IP interface brief, okay, we're connected to VLAN 10. VLAN 10 is defined. We have a locally attached host in VLAN 10, 10.10.10.200. But let's go ahead and take a look at how we would actually reach that host. In this case, we don't have it. Leaf 2A doesn't actually have that particular host route for 10.10.10.200. So let's go ahead and take a look at the VxLAN interface. We have the VRF to VNI mapping. do we have the mapping here? We have VRFA to L3VNI 50,001. Let's actually close this out to eliminate some confusion on our part. Then we'll take a look and say, okay, well, we have the symmetric mode of operation defined. There we go. 10.10.10.100/32, even if we're trying to reach, if we look at our diagram here on the right, leaf 2B, even if host C wants to reach host A, we're still going to follow the route as opposed to performing a local bridging operation to that remote host. Now, if both hosts are in the same broadcast domain, like host D to host A, then we'll, of course, still use a layer 2 VNI. We still support bridging functionality. But if we're crossing a subnet boundary in the symmetric IRB model, the takeaway is that we always follow the route. And the reason that we're taking a bit of time to cover this is because this has a major impact on hardware resource consumption as it remotes to remote host reachability. So let's actually take a step back and look at what this means. So we know that in the inner Ethernet header of a VxLAN packet that's used for a VxLAN routing operation in symmetric IRB, the L3 VNI is used in the VxLAN header. Additionally, we know that the destination MAC address, in this case, ending in 201D, that destination MAC address is the router MAC associated with the next hop VTEP that advertised reachability to that particular host. So in other words, this host is reachable via this VTEP with this L3 VNI and destined to this router MAC. But the interesting thing here is that the same goes for any host in VRFA that resides behind this pair of VTEPs. So for all 250 hosts, they're all in VRFA. They all exist behind the VTEP at this IP address using L3 VNI 50,001 and router MAC ending in 201D. So now we have a way that we have an N-to-1 mapping. So instead of 250 unique forwarding entries in hardware, because we're no longer bridging to these remote hosts, we don't need to maintain those in hardware. So at this point, we now can actually represent all 500 hosts via 2 forwarding entries in hardware, because ultimately the resolution, regardless of which host we're trying to reach, it's ultimately going to resolve to the same information regardless of which host we're going to. So this gives us our N-to-1 mapping. So if we take a look here, we'll take a pause and then we'll actually open it up for some questions before we jump into our proxy. But looking at our findings, a big piece of this was that when crossing the subnet boundary, we always perform a routing operation. And notice that we didn't really bring up the selective ARP model, because whether it's enabled or disabled in the symmetric IRB routing model, the entries for remote hosts, remember, we're following the routes. We don't need forwarding entries in hardware to perform bridging operations to remote hosts, because we're following the routes, which ultimately resolve to the same pieces of information, being the VNI, or the VTEP IP, the L3 VNI, and the EVPN router MAC associated with that next hop VTEP. And just to kind of level set, where does all this information come from? How did this actually populate into the routing table? We take a look at the dual label / dual VNI type 2 route. In particular, we're picking on host C again. We have his MAC address here. This is the MAC IP route, saying that this IP address is reachable via this VTEP, this L3 VNI, and this EVPN router MAC. So this dual VNI type 2 route is ultimately where this information was derived from. Okay, so I know we're moving at a relatively brisk pace. I want to take a second to pause before we jump into our proxy and actually open it up for any questions. So Alex, Alton, any questions out there?
So I think one question, and I think Vishali has answered that, was really the idea of why you would enable selective ARP, or why wouldn't you enable selective ID4? And I think Vishali was pointing out the answer to that really is down to scale, right? If you're running an asymmetric IRB model, And as the scale increases, there is a level of optimization. If you if you then enable selective ARP. Do you know don't know if you want to add to that, Mitch?
No, I think that's fair. You know, it's pick whichever model makes sense for the deployment, and then if we need some hardware optimization, then we certainly have that ability. So no, I have nothing to add. Cool. Anything else, or are we good to keep moving?
I think we're good, Mitch.
All right, very good.
Any questions in the chat?
Wireshark is barking at me here, so we're just going to remind me later. All right.
Thanks.
Yep. All right, so ARP proxy. This is commonly referred to as ARP suppression. But before taking a look at this in action, just as we did with the asymmetric and the symmetric IRB models and how they relate to forwarding entries in hardware, let's review this scenario. So we'll go at a relatively brisk pace through this scenario. But the idea is that host A is going to try to communicate with host B. It has no idea what MAC address it should put in the Ethernet header. So it says, all right, hey, who owns .200? That is, of course, an ARP request that's flooded, destination MAC of all Fs. And at that point in time, Leaf 1A knows via the type 3 routes received from remote VTEPs who needs to get a copy of this broadcast. So it creates a copy of the broadcast and then performs a VxLAN bridging operation, sending it over to the remote VTEPs that have expressed interest in receiving this. Once 2A or 2B receive it, they perform the decap operation and then forward it in the bridge domain they have locally mapped to that L2VNI, which, as we all know here, is VLAN 10. Okay, host D reply, of course, is unicast. The ARP reply comes in, and then it is just VxLAN bridging operation, still L2VNI 10,010, right back to host A. So the idea here with ARP proxy or ARP suppression is that we would like a way to reduce the amount of ARP requests that are flooded throughout the EVPN domain. And because the VTEPs have the MAC plus IP mappings associated with the remote hosts, the local VTEP can send the unicast ARP reply to a locally attached host on behalf of the remote host. So kind of whiteboard this out, and then we'll actually take a minute and watch it in action. A here says, okay, hey, well, who owns .200? Leaf 1A knows via the type 2 route originated for host D by Leaf 2A2B, it knows the MAC plus IP mapping of that respective host. Because it knows that, it says, all right, cool, well, I'm going to go ahead and reply on behalf of host D. And then when host A receives it, it has no idea. It looks like it came directly from that remote host, and we did not flood that ARP request across the EVPN domain. So that's pretty handy. Let's actually take a look at that in action. All right, so back in our environment, let's go ahead and first, let's do show IP ARP remote on Leaf 1A. And notice that we only have remote ARP entries for hosts D and E remote because we no longer have any presence at all on the bridge domain VLAN 30, nor do we have any SVI associated with it. But we still have the remote MAC plus IP mappings for hosts D and E. So in this case, we're actually going to say we're going to have A ping D, but first we're going to clear the ARP cache on A entirely and make sure we have no other pings running. And we don't. So let's go ahead and clear the ARP cache on our end hosts and then validate ARP-A. We'll just do that directly on host A. It currently does not have a MAC to IP binding for 10.10.10.200. Now, before we actually run this, let's watch the counters on Leaf 1A to make sure that we actually are performing the ARP suppression. So we should see that this should tick up from 76 to 77. Let's make sure this thing hasn't ARPed yet. It hasn't. Very good. Ping 10.10.10.200. We're only going to send one ping, but we're going to start our capture back up so we can see what actually happens on the wire. All right, so again, lots of noise. We'll filter that out. Come back here, send the ping, successful. Come back over here and take a look at what happened. The ping was successful. The request and the reply. And we saw ahead of time that host A did not have an entry in its ARP cache for host D, so it had to send out the ARP request. We didn't see it on the wire. Remember, this packet capture is happening on the interface 1 of spine 1. So if a broadcast frame was flooded and VxLAN bridged towards leaf 2A or 2B, we would have seen it. We see here that the ping worked just fine. Let's go back and actually look at leaf 1A, and we see that this ticked up to 77. So the ARP proxy, the suppression itself, was successful. So the question then becomes, what if we have a scenario where we don't want this behavior? We do not want ARP proxy to apply to a host or a range of hosts. And we can accomplish this via a feature referred to as ARP proxy exception. So let's go ahead and take a look at this. First, we'll actually take a look at the scenario. And again, fairly straightforward. In this case, rudimentary example, host A is just checking the liveliness of host D, and it's doing that via just ARP requests. Hey, who owns .200? If I get a reply, I'm going to go ahead and assume that that's alive. Fantastic. Well, that's all well and good, and we see here that leaf 1A is actually performing the ARP proxy for host D, and everything's fine. Host D is up, happy, live, good to go. But then now host D is the opposite of that. Host D has failed. But the problem is that until leaf 2A or 2B send the associated withdraw for that type 2 via BGP over to leaf 1A, leaf 1A is still going to have the MAC plus IP mapping for host D. It's still going to know about it locally. It's going to be on that output of show IP ARP remote. So it has the information to do ARP suppression, and it will. So host A is still going to say, hey, is D still alive? And leaf 1A is going to say, you know what? It sure is. Which we all know here that that's not the case. So this could severely impact failover operations. So in some cases, we may want to provide an exception to the ARP proxy / ARP suppression functionality. And in order, let's go ahead and do that. All right, so over on leaf 1A, we actually have a prefix list defined. This prefix list, it could be multiple sequence numbers. We can get pretty creative. But in this case, we kept it pretty simple. A prefix list for host D in particular, what we're going to do is exclude this from the ARP proxy functionality. So the important takeaway here is that this needs to be a deny. So if we go in here to leaf 1A, and we again go back into router L2 VPN, and we do ARP proxy, and then the prefix list, PL host D. What we'll do now is go through our previous example again, but what we should see is that the ARP request in this case does flood. It's not going to be suppressed by leaf 1A. So let's bring up a couple counters to first validate that we're seeing what we expect. So this is still at 77. This is currently at 3. After our example, we should see that this is still at 77. And then this should increase to 4. Okay, so let's go over here and actually clear the ARP caches. And then we'll go ahead and restart our trusty packet captures. Actually, if it's still rolling, that might work. Let's go ahead and do this. So ARP, we do not have it resolved. Ping 10, 10, 10, 200. I think we actually stopped the capture. Did. So let's restart it. All right, and we'll apply our filter, and we'll authenticate. There we go. All right, filter applied. Now, let's execute our ping. And we'll just do a couple of them, simple. 2 pings. What we see here that now the exception occurred. So we can stop this and say, we didn't see this in the previous example when ARP proxy functionality was enabled. Now we do. We see that this broadcast frame here is being VxLAN bridged towards the VTEPs that have expressed their interest via type 3 routes for bum traffic associated with this particular VNI. In other words, it's a fancy way of saying, hey, I want the broadcast traffic associated with this VLAN. So we made sure that those VTEPs did get a copy of this broadcast because we're not suppressing it anymore. And then, of course, host D receives it and crafts the unicast reply saying, hey, by the way, that's me. send that to my MAC address, and then the pings roll. Let's go ahead and check our counters and make sure that they did what we expect. Leave 1A. This is still at 77, and as expected, this has ticked up to 4, indicating that a ARP suppression exception has been denied due to the prefix list / ACL we have applied to the router L2 VPN configuration context. Okay, so I would like to pause for any further questions. Alex, Alton, any questions related to ARP proxy?
No, I think we're good. I think.
Okay, very good.
Oh, sorry. Just one quick question, mate. There was a question there. Just saw the kick come in there. I noticed. Can we disable ARP suppression on a particular VLAN or a prefix?
For a particular VLAN, in that case, we would end up using a prefix list that would actually call out the range of that respective broadcast domain subnet. So if we want to exclude VLAN 10, we would say, all right, well, the prefix list would be, in our case, VLAN 10 is 10.10.10.024. We would add that to the prefix list, and that would effectively disable ARP suppression for that entire VLAN. Does that make sense?
Makes sense to me, Mitch.
Okay, cool. No, good question. All right. Any other questions?
No, I think we're good, Mitch. I think there's been a few questions. We will post at the end of it, obviously, the video, and there's been some questions regarding the previous video, and also I think there's been someone looking for the config guides and such like. I think we can put them in email, such like. But I think, are we finished, Mitch, or you get something else to cover?
No, that's it. So we did pretty good on time this time around. Look at that. Did want to call out what's coming next, and that we have the dual homing with MLAG and EVPN, the active-active dual homing without MLAG, and then scaling and, of course, multicast. So I do want to say, everyone, thank you again for joining. Again, keep on the lookout for an invite to the next session. And with that, I will turn it back over to Whitney.
That's all the time we have. Thank you so much for joining us today. If we did not get to your question, please feel free to email us at webinars@arista.com. Recording of this webinar will be available on our website.